slides we will run different tools. So we got to the part where we kind of wrote out the unwinding dilemma. I think I had a typo on the board yesterday, but so I put in two references here. I will upload the slides also. I have notes for the proof. I'll turn them into PDF. I will upload in the Slack channel so you guys can take a look. So basically, for PL, a lot of times we can see how other people prove things. But in terms of the paper I put in here, their setup is different. So the way I set up the semantics, they are different from what this paper are setting this up. But the high-level structure is the same. You have inductive proof, you have this unwinding lemma about one step. So those parts are similar. But in terms of semantics, some use big step semantics, some don't necessarily use the context the way I use context, so I can have a flash trace. Sometimes you just use congruence rule for sequencing, so you have a different way of defining traces. So basically, these are for references. If you want to do the exact proof that I set up to do, I just read the PDF I put in the channel. That's probably the best place. But in general, for PL, you do your own definition, right? As long as in the end it's correct, right? So there's no reason why we have to do the exact same thing other people are doing. Okay, so basically, just to wrap up this part of the lecture, so we had a simple language. Now, what's missing is we didn't really talk about first-order references. We also don't have first-order functions. So these are actually useful things. So therefore, we can extend our language. So because when you go into higher-order case, there isn't necessarily a reason to distinguish between expressions and commands. So here is your typical blah calculus. So here we're just going to have, this is like the new, I will generate a location on the heap, and I'll store the whatever E value to that store. So here we're going to give the type here. So we're going to mark the type of E in here to help. Wait, sorry, do I need E or do I need? Yeah, anyway, so basically the expression, I have a few notations to help me do the typing. And then I don't need sequencing anymore because let is actually sequencing. I also don't need let. Applications the let can be sugared into application anyways, but to be convenient, we're going to have let. So now for type, because I have higher order functions, now it's more meaningful to actually have type in there. So we still have the type we saw yesterday where we have Intel. Now we have a rest type also. So this is actually really just talking about a integer or a expression that will evaluate to an integer that have a secrecy label L or security label L. And these are references. The reference themselves have a label L. The value stored in the reference has type tau. So you can imagine type tau itself have an L also. So you can have a location that the location's label might be low, but the content stored in it might be high, for example. Right? So some of these messing of label doesn't make sense, so technically we'll rule out of it. But in general, for a reference, you're going to see two labels. One is about the pointer's label, the reference label themselves. The other one is the label of a value that's stored in the pointer in the reference. Now for function, I have even more labels. So function typically you just have tau or tau, argument type, return type. Now I'm going to add this L is the security label of the function itself. Is the function itself secure or contain secrecy or not? So this interpretation, after debate, so sometimes people think that you can't actually inspect the function. The only way you can use the function is actually call it. So people treat this slightly differently. But this is one way to do this. Just add label whenever you think actually makes sense. And then the fourth label we have, so basically I have four labels because argument type actually have a label, the return type have a label, the function themselves have a label. Now we also have a context label because we're going to call the function in a certain context. Right? So we're going to specify what's the label of the context that I can call the function. Right? So that's a typical way of setting up the higher order references, first class references, higher order references, and first class functions, or higher order functions. So again, different system do is slightly different, so I'll give you one version of this. So when I allocate a new location, so basically I need to give a label to the reference, right? So here the programmer didn't tell me what's the label of the reference, So one way to do this is to decide the reference based on where I did the allocation. So here, PC is the context under which I'm executing this new, or this allocating this location. Therefore, the reference will inherit the label of the context. So that's one way to do this, right? So I'm going to pick the PC label as the label of the reference. Right? That's enough to protect this reference itself. So for function, so here, I didn't use fix. You can just imagine this is a recursive function. E can contain f. So here, in the function definition, I'm going to already assume the programmer gave me the argument type. The programmer also gave me the context in which the function can be called, also the label of the function itself. So I have all the data, so I don't have to figure out what they are. So this is, beyond that, this is actually a pretty typical rule, right? So I'm going to type check the function body to have the type of the function body, and then inside this, the argument x will have type tau as specified. This f will have this type. We're just going to drop this entire type in here so we can type check recursive functions, right? So we're not using any label in this type checking yet. We're going to do some label check when we use the function. Yeah.
So the PC prime, is that just an arbitrary PC, or does it?
Yeah. So this PC prime is where you define this function, but this is not where the function is called, so I'm going to ignore it, right? I will check the function body based on where this function is called, because that's where E will execute. So I'm going to take the PC as specified by the function to check it. Yeah, because I'm defined this here, but where it's defined doesn't really leak any information. So I'm going to drop this PC prime. Yeah. Other questions? Okay, so this is the function application rule. So E1 apply to E2. E1 is the function, so it's going to have this function type with all these labels. Again, this PC prime is the context in which the function is being called. And then we'll check the argument type that has type tau, also on the same context, PC prime. So here is where we're going to do some label check, right? So now is the place E actually execute, right? So what the programmer said is that the program should run under the context PC. Now there is the PC at runtime. I have to compare them. So basically, I enforce that the current context PC prime has to be lower or equal to the PC, right? So basically, the programmer said, hey, this program needs to run this function needs to run in low context. Low context is the issue, or high context issue. Yeah, if I'm running on a low context, that means I'm going to do, the function is going to do a bunch of assignment to low variables, right? So if I'm calling the function in a context that actually does not allow me to assign low variables, that's not going to work out, right? So therefore, I'm going to enforce this constraint that the current PC needs to be lower or equal than the PC the function specifies. All right, so that's one constraint. The other constraint is, so this one again is arguable depending on whether you think function is inspectable or not. So basically, what this is asking is that because the function is executing under this PC, this L, this function itself, the PC should protect the function's label. So that's kind of how this is reading. This rule can be checked slightly differently. This is one interpretation to make sure that you're not accidentally leaking information through the function label in some sense. Equally, you can also protect this label in S, because that's actually where you see the return value. And that's alternative interpretation here. So these rules are not straightforward. I think the easy way to check this out is try a few alternatives and write a program that might leak information to see how these constraints help you rule out these programs, also help you allow good programs to be type checked. So these are the two things you can check to test out your rules. Okay, so I'm not going to do more proofs here. This has been done for different languages. I have a summary of what information flow types have been done to what languages. But this set of rules I've taken from a paper on information flow type system for OCaml. So when you deal with OCaml, there are also event handling. That's actually tricky also because you change the control flow, you might leak information. So we're not going into details over there. But it's just to show you that for information flow types, yes, if you have first-class references, if you have first-class functions, they can be handled also. But the constraints sometimes can be a bit complicated. All right. Okay, so in terms of the agenda, we kind of finished the last part. I think it might be a little bit ambitious trying to finish all of the right parts. I might skip some of the content. So we're going to quit the type system, the enforcement part a little bit. We're going to go back to address what do we do with having to leak some information for the program to actually work. Right? So a lot of the examples actually need downgrading. Right? So we saw many of those examples in the first lecture. So your password checker definitely leak information when you type in a password. The checker would always tell you whether you enter the right password or not. Right? That decision, depending on this secret value password, the strict information flow property would prevent a good password checker to be type checked. Right? And then things like releasing aggregated data. Right? So the Strava map, in fact, for different reasons, but in general, heat map, this kind of aggregate data release statistics is considered to be okay. Right? So we have to allow this somehow. Other things like the conditions under which you're allowed to see the data. Right? So for example, if I pay, now I can see the next movie. If I don't pay, I cannot see the movies. Right? If you think about it, the movie is considered secret. I can only have access to it once I do payment. So it will release to me when some condition is being satisfied. Right? That's the secrecy side of things. For integrity, you have similar issues, right? So it's very rarely that program does not interact with untrusted data, right? If you think about your OS, your system calls, actually clients will call into system calls, right? The applications will call the system call, providing arguments coming from the application. If you think of strict integrity enforcement, this argument should be used by the system call period because who knows what the argument contains, right? But in reality, that's the functionality OS provides. So in reality, a good OS programmer in their API, they would sanitize or check the input to make sure that bad things won't happen, right? So when you check it, what you're doing is you're actually, after you check it, you endorse this data coming from untrusted source because you know that it's okay because I checked, there's no problem with this data, I can use it. Right? So that operation itself cannot be allowed in a strict non-interference definition. Right? Other things like we all download programs from the internet. Right now, all the apps are in the App Store, so we have download program from the internet. And every time we can open the program, most OS would ask you, are you sure you want to run this program? Right? You click on OK, it's an explicit endorsement operation. So now it's okay because some of you thought about it and decided this is a good program. So obviously leaving this to human judgment isn't necessarily the best thing, but the operation itself is a sanity check, is an endorsement method so that we can actually run programs as intended. Right? Again, non-interference wouldn't allow us to do this at all. Because running the program, actually the program itself do come from untrusted sources. Okay, so how do we do the declassification, right? So adding operation is easy, right? So I can just say, hey, I want to declassify this expression E. I want to declassify E to a label L, right? So if I have 2-point letters, I'm going to declassify E to this low label, for example. Right? So the question is, if I put this operator in my program, now what can I say about the security properties? Yeah?
Nothing? Like you can declassify anything if you're just putting the operator in there?
Yeah, what's the best we can do is still say something. We're formal people, we need to know what's the guarantee. Now that I know I don't have non-interference, you have declassification. Yeah?
Whatever is declassified, it can now affect the final output.
Yeah, so the easier way to say this is saying if your program doesn't have declassification, non-interference still holds. Right? So that's the easy way to prove it. So for a while, the community essentially, in the information flow security research community, whenever we have designed a system allow declassification, that's probably what we're proving. We're saying, hey, if I don't see any declassification operation, I should have non-interference. Right? This isn't a very good theorem because it doesn't say anything about declassification themselves. If you have one, now is a point where I can't say anything anymore, right? So I want to be a little more precise about how to say this. So this one, our early papers kind of try to be a little more rigorous. This is delimited release. So this is a little bit more syntactic. So the idea is that I'm going to syntactically look at my program. And I look at my program contains exactly these declassification operations, right? I don't know whether they will all be called or not, but I saw them in my syntax. So in the worst case, all of them will be called. So let's say that I have n of such operations from declassify E1 to label L1, so on and so forth. Right? So this is saying, now instead of they're saying, if I don't have declassification, I'll be okay. What this is trying to say that if I declassify, if I have two runs that end up declassifying the same value, then I can't sort of still have 9 difference, right? So basically, I'm quantifying what the attacker is allowed to distinguish once I have declassification. If the two declassifications end up declassifying different value, I can't say much, but if they declassify the same value, we still should have 9 difference. So I wrote this out, so let's take a look. So again, I have this attacker's label LA, any label, and then I have two memories that's low equivalent. I dropped the gamma just to be a little bit quick. So we always have to use the type gamma to know what's high, what's low, and so on. So these two memories are equivalent. So typically, 9 difference will just go to the bottom saying, hey, I evaluate C, end up having two resulting memory. The resulting memory should still be equivalent. Now I have to say more. This is not true anymore, right? Because I have declassification. So instead, I additionally said that not only that, these two memory you give to me, when I evaluate this declassification operation, the result of these has to be equivalent based on attacker's observation. This is the operation we defined in the previous lecture. Right? If this Li is observable by the attacker, this has to be evaluated the same value. If this label is not observed by the attacker, I don't really care how the relation of the values. Right? So this says a little bit more about declassification. Right? So we can go through an example. I think I can right here. Get our simple program. So basically, let's say that I have a variable. I'm going to declassify. Always easy one. One model 2, right? So and then I'm going to let's say that I don't have output here. I'm still marking memory. Too low variable. So here, I'm explicitly saying that this is what I want to declassify, right? So now, if I have memory, that map y to 0, I have one memory map y to 1. I can still see a difference, but this is because the y mod 2 for these two memories they're different. But for 9 difference, I don't care about these pair of memories. Instead, I care about all the memories where this is 0, 2, 4, so on and so forth, right? So the attacker cannot distinguish between this set, also this set, 1, 3, so on and so forth, right? So this is saying that this declassification allows me to tell me I'm in this half or in this half. But once I'm in this half, I can't tell what's going on. This is okay. Right? So this is what this declassification definition is saying. Any question about this? So get a little more precise. Yeah.
So I think I'm having trouble understanding how we're reading sigma at EI, and we're saying that that's equivalent.
We evaluate each EI under different memories.
Okay.
Yeah. So if I take this memory, I evaluate y under this one. They're the same value when I mod 2. They're both 0. Right. So for all the memory that's in this set, right? And the ending memory should be the same,
Okay.
right? So which is true. The x will be 0 here, x will be 1 here. Yeah.
But all the expressions evaluated at the initial state.
Correct. Yes. So here, actually, if you read the paper, it basically said that before declassification, you're not allowed to modify any variable that we use in declassification. So that makes our life a little bit easier. Otherwise, we use dependency analysis to figure out what's actually being declassified. Yeah. So here we're going to assume when I say declassified, that's the initial value of declassifying. Yeah. All right. So now I already mentioned this is like statically looking at code, grab all the declassification operation out of here. What's the limitation you can think of? Any limitation you can think of? Yeah.
If something is conditionally declassified?
Yeah, so basically, I don't know whether this will execute or not, right? So I can write some program. Let me read this up, I don't have much real estate. This is like a simple example. It's half, so it's easier. That's what example I have, so I don't have to think about it. Okay, I'm going to have two programs. So the first one is saying, let's say that I'm asking for some payment, right? If this payment, let's say greater than 10, let's do less than 10. What I'll do is I will I'll shorten declassify, so I don't want to write too much. I'm going to declassify the pilot. This person is trying to ask for some show, right? This is one episode, first episode of the season. Otherwise, I guess this is like, right. I think greater than is easier because then I have to bound the lower bounds. Anyway. If it's greater than 10, I will give you the whole season. Otherwise, I'm going to declassify just the pilot itself. Right. This is a sensible program. Now I'm going to have another program. I'm going to say if in the same condition, this payment is greater than $10, m equal declassify season, and then else pilot, and m again declassified season. Right, so these two programs, if you look at it, is different, right? This is actually a broken program, right? This is a program meant to be, if you pay more, I give you more episodes. If you pay less, I'll just give you the first one. This one is saying, well, if you pay more, I'll give you the whole season. If you pay less, I'll first give you the pilot, then I'll give you the whole season. Right? Now I look at the declassifying operation, the same operation. They don't have differences in terms of operations, right? So now both of them will specify this property, so they're syntactic. But this actually conditional is important. When, where you actually do declassification is fairly important. Right? So this definition is not without flaws, but it's better than saying, oh, if you declassify, I don't know what's going to happen. At least I will say something there. It's not very tight. The condition is not tight. Okay, any question about this? Okay, so now I'm going to move on to a different definition. So basically in the information security field, now most people like this knowledge-based definition because it's more intuitive, right? If I tell you two numbers are the same, but it's a lot more intuitive when, in the previous example, I draw on board, hey, here is 1/2 of the space where, you know, y is 0, 2, 4, and so on. And I have another half of the space, which is 1, 2, 1, 3, 5, and so on. And the attacker knows which half is in. So that's intuitive understanding of what's been leaked, right? So knowledge is meant to describe that, to be more intuitive. This is in terms of secrecy, obviously. So I will not touch upon integrity. Integrity is always a little bit weird. Secrecy is more intuitive, so we're just going to stick with the secret side of the definition. So knowledge is about, if you think about it, you have secret, right? So for example, an integer, 32-bit integer. If it's truly secret, it should be the case that as the program runs, you ask the attacker, hey, what's the secret value? The attacker's knowledge should be a full set of 2 to the 32 possibilities, because the attacker couldn't know which value it could possibly be. However, if I go through declassification, like the mod 2 declassification, after seeing that value, now the attacker's knowledge gets refined. Now the attacker knows half, eliminate half of the possibilities. Right? That's the notion of knowledge. Sometimes people say knowledge represents the uncertainty of the attacker. The more uncertain the attacker is, the more secretive the better off you're protecting your secret in some sense. Right? So basically, when I use knowledge-based non-interference, I would also allow, so if I do truly non-interference, the attacker's knowledge should never change, should always be all possible values of the secret. If I allow declassification, then I would say, one, I will allow the attacker to refine its knowledge. Right? So here is the example. I should have had this example earlier. So I have two programs. Again, X is public, Y is secret. Let's forget declassification for now. Let's just look at programs property in terms of knowledge. So here, if I directly do explicit assignment, before running the program, let's say that X is 32-bit integer. Before the assignment, the attacker knowledge is the full 2 to the 32 possibilities. After the assignment, the attacker knowledge drops to 1, very specific knowledge, right? The attacker knows exactly what's the value of Y, right? You see a drop in knowledge. So you can see that this program, if I try to enforce strict non-interference, is leaking information till the attacker gets to refine the knowledge. So the next program also does not satisfy the strict non-interference, right? So after seeing the output, initially Y again is 2 to the 32. After finish the program, looking at what X is, now the attacker can cut the knowledge by half, right? The possible set become either greater than 0 or less equal than 0, right? So that's a refinement of knowledge. Okay. Let's see what else. Yeah. So these programs typically would declare them not secure because there's no declassification in them, right? The knowledge is getting refined, so that's bad. Now, if I have this program, I'm actually properly have gone through declassification of X. So here, this program is okay, but I have to specify what does it mean by this program is okay. I will show the definition later on. But intuitively, the declassification allowed me to know that Y belongs to 4 parts of this value space, right? Either not 4 being 0, 1, 2, 3. Right? So that's refinement that's been allowed. Okay. So that's the intuition. Now we can do a little more definition. We're going to change definition later on. So now we're still having a command. I have a, let's see. Let me see if the definition is actually correct. So the subscript. Yeah, so okay, when I do traces, this is slightly different. So here, the way we define knowledge of this program C, we give a starting memory that I'll run the program C to begin with. So the knowledge of the attacker after running the program is such that for all the memories sigma prime, that's low equivalent to sigma, and they end up being a final state that are low equivalent. Right? So that's one way of defining the knowledge that the attacker will have at the end of running the program. So here I have one shot, right? So I'm starting. So this is necessary in that the attacker can always only observe the memory that's equivalent up to the memory they're given. Right? They don't know secret, but they know what are low values. Now, running C would allow them to refine the memory because in the end, the final memory, the ones that are different, they know that it's not possible. They're ruling out certain parts of the memory by doing the final observation, right? So now I can also define an initial memory. So the initial memory is the one, if the attacker sees the initial memory, you ask the attacker what's the secret value. This is a memory secret prime such that they're low equivalent to sigma. I dropped the A, but yeah, should be LA here. Right, so this is like, without running the program, attacker just seeing the memory itself, it knows that other memory is not possible by looking at the low value. But in theory, they shouldn't know anything about the secret value. After running the program, seeing the final memory, the attacker now has more refined knowledge. So now the security condition, the strict non-interference, this is saying that if the program is secure, means that if I run the program, this knowledge set should not be more, we actually not refine the knowledge compared to the initial memory. Right? So the other direction is implied. As I run the program, I have more observation. Typically, you get to refine the memory. Yeah.
Just to make sure I understand, knowledge is modeled as a set of sigmas or as one sigma?
Set of sigmas.
Okay.
Yeah, the set of sigmas, possible values. Yeah. Or possible values. Yeah, so in the XY example, you can think of the set of X and Y's mapped to different values. Because X is low, they're always the same, so really what matters is Y. So the if-then program, initially the knowledge is such that X is equal, but Y can be any value. That's all the possibility you have. After running the program, now X is, by looking at X 0 or 1, you know Y is greater than 0 or less equal than 0. Right? So this knowledge is smaller, therefore it violates this definition. Right? So it's not non-interferent in the previous example. Yeah.
So smaller knowledge actually means knowing more.
Yes.
They know, oh, okay, it's like a sharper.
Yes, yeah. If I know Y is exactly 1 versus it can be either 1 or 2, right? Being 1 is being more precise, leave more information.
Okay.
Yeah. Right, other question about this? Yeah.
In the first knowledge definition, the set which is the set of sigma prime, or why is it not the set of sigma prime?
The first one?
Yeah.
So the knowledge is always, yeah, so yeah, this is a bit, are you asking about why I care about initial memory? So here the assumption is the secret is in the initial memory. That's why assumption we're making. Like you set the password, that's what we're after. Yeah. If you want to be more refined, we will go to a trace-based semantics, so that's what we're going to do. But in this trace-based semantics, I actually don't have dynamic secrecy. This is a dynamic secret. But in general, you can see that I can actually change my program. So here, I'm going to, as the program execute, think about semantics that we had yesterday. Every step I make a transition, I also emit an action saying, what did I do in this step? So typically, I don't really care about anything, your assignment, your branching, your sequencing, I don't really care. I care about declassification because that's one operation that the attacker, if declassified to low, the attacker actually can see that value, right? So that's important for me. Now I'm going to add the output. I will kind of sort of use output on and off. Let's say